In this video, we're going to take a slight detour on our journey through these special continuous random variables. And the detour is going to take us to something called the gamma function. And we need this function in order to define a couple more special random variables. But this function in its own right is a function that plays a very important role in many branches of mathematics. Some that are very theoretical, others that happen to be rather applied. So this is not a function that you would have seen before. It's a new function. It has lots of different properties, and there are just a few that we need in order to be able to work with some other special continuous distributions. So what is this gamma function? Right, well, here's the definition. So for alpha greater than 0, the gamma function, right, and it's denoted, it's uppercase gamma of alpha, so is defined by, and this is what it is. So this is what we're defining, and it turns out this is a function that is defined in terms of an improper integral. So it's the integral of from 0 to infinity of x to the alpha minus 1 e times e to the negative x dx, right? Now, it turns out that this improper integral, it can be shown it will always converge, right? For alpha greater than or equal, alpha greater than 0, this improper integral will converge. But we're not going to really talk about the convergence of it, but we want to be able to evaluate this, right? Now, since this is an improper integral, what I'm going to focus on is, let's say we consider this integral from 0 to b, right? And then at the end we'll take the limit of this to see what happens. But so let's say we have to integrate from 0 to b, and the function is the same, x to the alpha minus 1 e to the negative x dx. Well, integration by parts is what we would choose here, right? And we would choose our u to be x to the alpha minus 1, and then our dv would be our e to the negative x dx. And we could set this up in the form of a table, but we're only going to do this parts once, and let's see what happens. So our du in this case would be alpha minus 1, so bring down the power, and then subtract 1 from this, and that leaves alpha minus 2, and then that's dx, right? And then my v is going to be negative e to the negative x. So when I apply integration by parts, so therefore this integral from 0 to b of x to the alpha minus 1 e to the negative x dx, that can be expressed like this. So it's uv, so it's my x to the alpha minus 1 times negative e to the negative x, right? And then minus the integral of v du. So then I have my negative e to the negative x, and then times my alpha minus 1 times x to the alpha minus 2 dx, right? And then I can't forget my limits here, right? So this will be evaluated from 0 to b, and then this also from 0 to b, all right? Okay, so this is kind of a mess, but let's see what we can do on the right-hand side. So I'm going to write this as negative x to the alpha minus 1 times e to the negative x, evaluated at 0 and at b. And then over here, I have a couple constants that I can factor out, because I can take out the negative sign, which makes it a plus. And then I can also take out the quantity alpha minus 1, because that's just it's just a constant, right? So I can take out the alpha minus 1. And then I'm left with the integral from 0 to b of the, let me put my x to the alpha minus 2, and then I have e to the negative x dx. All right. So on this part, we still have the integral, right? But I have this extra alpha minus 1 out front. And let's go ahead and evaluate this, right? So when I plug in my upper limit, and I remember I'm plugging it in for x. X is my variable of integration here. Alpha is just a parameter, it's just a constant. So when I plug in my b, I'm going to have negative b to the alpha minus 1, and then I'll have e to the negative b. So that's at my upper limit. Then at the lower limit, when I plug 0 in, well, that's nice because I have 0 raised to some power, and that's going to be 0. So I have minus 0 there, and then I still have my remaining term right here with the integral. Right, so then we have our x to the alpha minus 2, e to the negative x dx. All right. So this part of it works out to be negative b to the alpha minus 1 over, if I use my property of exponents and rewrite this so that I don't have a negative in front of my exponent here, this becomes e to the b, and then I have plus alpha minus 1 times the integral of 0 to b x to the alpha minus 2 e to the negative x dx. Right? So that's what this is. So now to get the actual gamma function, I have to let b go to infinity. So what happens to this expression as b goes to infinity? So the limit as b goes to infinity, let's focus on this part. Well, actually, let me put the limit in front of everything here, right? So let me bring this term down. So we'll have this x to the alpha minus 1, e to the negative x dx, and then that would have to be equal to the limit of this. So this will be the limit as b goes to infinity of this term, the negative b to the alpha minus 1 over e to the b, and then plus, and then I'll have alpha minus 1 times the limit as b goes to infinity of the other integral. So x to the alpha minus 2, and then e to the negative x dx. So let's go term by term to see what happens with these, with the limit. Well, this is, this is our definition. This is the gamma of alpha, because as b goes to infinity, I would get that improper integral. So I would have this. So 0 to infinity. And then that's exactly how we define this gamma function. And then I'll have my x to the alpha minus 1, e to the negative x dx is equal to, now what about over here? Well, the thing is that if for instance we assume that x is, so for instance if alpha is positive, then I guess we could do two cases here. If alpha is strictly greater than 1, then what we have here is a power function where the exponent is bigger than 1. So we have, in fact, in both cases, we're going to have a power function at the top, right? So this is a power function, and this is an exponential function. Now, which of these will grow at a faster rate? The exponential function grows at a faster rate, right? In fact, we could formally use L'Hopital's, and what would happen is the denominator here would always dominate this fraction, and the denominator would get arbitrarily large, and the numerator will be kind of trailing back. So this fraction, this whole fraction here, is going to approach 0, right? Because you have your exponential growth in the denominator, but only your power growth there in the numerator. So that first term, that's equal to 0, and then plus, and then what do I have here? I have alpha minus 1, And then this is just another improper integral, right? So let me write it here. So it is the integral from 0 to infinity of x, and then what we have here is alpha minus 2 e to the negative x dx. Now this is pretty interesting because by doing parts, we've come up with this relationship. If you notice, the only thing different from the original gamma definition is the fact that this exponent here is alpha minus 1 and this one is alpha minus 2. So if the gamma of alpha is defined this way, then this integral over here should be another gamma function, but just notice that this, or let me say it this way, this exponent is 1 less than this exponent, right? Pretty interesting, right? So this power is 1 less than this power, so that means this improper integral represents the gamma of alpha minus 1, right? So take a look at that. So I can write this. So in fact, let me write it below. So this is our definition of our gamma function. The 0 I will ignore. And then here I have the quantity alpha minus 1. And then what I have here is another gamma function, but with alpha minus 1 as my argument or my parameter. So like this, right? So we've just proven that using integration by parts, that the gamma of alpha is alpha minus 1 times the gamma of alpha minus 1. And this is a recursive property, right? Right? Now, but let's really think about it. So suppose our alpha is a positive integer, right? So suppose alpha is equal to n, a positive integer. Well, what does that mean? Well, let's see if we can apply this recursive property and come up with another useful property. So if we start with the gamma of n, a positive integer, so then what we would end up doing is subtracting 1 from that, and let me write that equal sign here. So this will be equals, and then it will be gamma, come on, of n minus 1. But then what if I apply that definition again, right? Oh, wait, okay. No, let's fix this. So it's n minus 1, there we go, times the gamma of n minus 1. But then bring down the n minus 1. So what if I apply this recursive property again? So now this gamma can be written as n minus 2 times the gamma of n minus 2, right? So that's what this is, right? But then I can continue applying that recursive property to each time I get a gamma function. So I have a gamma, it's a nice positive integer. So now gamma of n minus 2 would be n minus 3 times the gamma of n minus 3, right? So basically what I have here is now here. Again, let me do this a couple more times so you can see the property. And then I have n minus 1, n minus 2, n minus 3. Now when I apply the property to gamma of n minus 3, I'm going to have n minus 4 times the gamma of n minus 4. So again, this part here, gamma of n minus 3, is n minus 4 times the gamma of n minus 4. And what will happen is eventually I keep multiplying by, if I keep subtracting 1, eventually I will get down to 1, right? Because if I start with a positive integer and I keep subtracting 1, because that's what I keep doing, I have n minus 1 times n minus 2 times n minus 3 times n minus 4. Eventually, the product, this product, or we can actually say this factorization, so eventually, and formally, we would need something called mathematical induction to make it a formal proof, but we can see the pattern. I'm just using this to establish another important property. So eventually, this factorization becomes this. So let's write it out in its fullest. So the gamma of a positive integer is equal to that integer minus 1 times that integer minus 2 times that integer minus 3 times that integer minus 4 dot 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 times 3 times 2 times 1. And what is this product? You've seen this product before. In fact, this is a factorial. It starts with n minus 1 and you multiply all the integers, all the positive integers, until you get to 1. So what we have here is this really remarkable property. So for every positive integer, the gamma of that integer is equal to the n minus 1 factorial of that integer. All right? So what does it look like? So for instance, if I wanted to compute the gamma of 3, so let me write down what the improper integral would be. Right? The gamma of 3, by definition, would be the integral of x to the 3 minus 1, so that's x squared times e to the negative x dx. But then we would have to go through what we did initially, right, and do our integration. In fact, in this case, to evaluate it, we would have to do integration by parts twice, then deal with the improper integral. And what would we end up with? Well, we would end up with what this says. We would end up with 3 minus 1 factorial, which is 2 factorial, which is 2. So the gamma of 3 is 3 minus 1 factorial, which is equal to 2. And this could work for any positive integer. So if I had let's say I wanted to find the gamma of 5, by definition, it would be this. The integral from 0 to infinity of x to the 4th power e to the negative x dx. And then again, but now using this property, because we have our a positive integer here, right? Then it's 5 minus 1 factorial. So that's 4 factorial. And that works out to be, remember how you compute your factorials, 4 times 3 times 2 times 1, so you end up with 24, right? So this is really the property that we're going to use the most. We're not going to rely on the improper integral every time we have to evaluate it, right? We'll use this property when we have to compute the gamma of certain numbers, right? Now you might ask yourself, well, what happens if the number isn't a positive integer? Then that's when it becomes interesting, and we won't really say much about it. However, there is a rather remarkable result, right? I'm not going to go through the proof of this result, but I think this is worth seeing, just if you're fascinated with numbers and just how math can throw really obscure things your way. So if you had to compute the gamma of 1/2, right? So again, this would be the improper integral that you would use to compute it. So it would end up being, so your alpha, well, in this case, it would be x to the 1/2 minus 1. So then you'd have a negative fractional exponent right there, and then you'll have e to the negative x, and then dx. Now this integral, right, is much tougher to do than these, right? These you could do your standard integration by parts. Yeah, you'd have to do it many times, as this integer power gets bigger. But if you have a fractional power there, it's like, whoa, what do you do? Well, it turns out really remarkably that this integral converges to the square root of pi. Just really, I mean, just absolutely fascinating that it works out this way, right? Now you could use this along with the other recursive results. So the other recursive property, right, that I mentioned right here, to find other values. So for instance, let's say I wanted to find the gamma of, let's say, 5/2. It's not a positive integer, so I can't use the factorial, but what I can use is I can say that this is 5/2 minus 1 times the gamma of 5/2 minus 1, which in this case would be 3/2. Right, so I could do this. So then I'd have 3/2 there, time, oh, not 3/5, 3/2. So 3/2, the gamma of 3/2, right? It's like, okay, great. Well, again, use the recursive property again. So this would be 3/2, and then I would have the gamma of 3/2 would be 3/2 minus 1 times the gamma of 3/2 minus 1, which is 1/2. So then what would I end up with? 3/2 times 1/2 times, and now I just told you, I didn't prove it, right? But I feel like you would trust me, right? Because I wouldn't mislead you with something so beautiful. But the gamma of 1/2 is the square root of pi, so then I'd have my square root of pi there. So that means the gamma of 5/2 is 3 square root of pi over 4, right? Now you might be wondering, what's the gamma of 1/3, or what's the gamma of 3/5, or something like that? Well, again, those would be tougher, and there are ways you can evaluate it, right? They're actually cool techniques that rely on complex integration that can actually help you prove some of these particular results. So these, like this particular result, it's just me showing you something, and again, something pretty remarkable in math. It's not a result that we're going to be using as far as helping us to compute probabilities. The main property that we need is this particular property that says if we have a positive integer, then the gamma of that integer is that integer minus 1 factorial. Right? And this we can do, and this will play a key role in the probabilities that we have to compute with the upcoming special continuous random variables. All right, so there's our gamma function. A very brief introduction. Hopefully you found it interesting, and let's see how we can use it going forward. See you in the next video.